Okay, thank you, Cohesion. Hello, everyone. So I'm going to present results from a project I had with USDOT PHMSA a number of years ago. It was one of my first projects. And you know, this session has been really wonderful where talks have been furthering understanding, or showing exceptional effects of these nanomaterials, optimization, synergy. This talk isn't going to really do too much of that, but we do still have some interesting takeaways, so I'm excited to have the opportunity to do that here. So I'm going to look at I'm going to talk about, this really was a performance-based study that looked at the effect of nanoclays, CNTs, and their combination on paste and mortar systems that both incorporated and didn't incorporate SEMs, specifically fly ash and slag. And so there's already been a number of talks that have covered CNTs, explained by the experts, so I'm not going to provide any background there, but obviously there's a lot of exceptional properties that they can introduce to the mechanical properties as well as electrical and thermal properties. But nanoclays haven't been talked about, so I'll provide a little bit of background there. So nanoclays can include any nanotype that has a dimension at the nanoscale. But in my presentation, I'm going to specifically be referring to a chemically exfoliated form of polygorskite attapulgite clay. And this material has been found to be a very effective rheological modifier, specifically in enhancing thixotropy at very low dosages. And this really is tied to its physical properties. So they're nano, they're 30 nanometer in diameter, 1.75 micron in length, and they have unlike charges on their faces and edges. So as a result, they can undergo significant shear thinning under shear and then exhibit rapid recovery at rest. And when introduced into cement-based systems, which are inherently also thixotropic, they've been found to have a significant enhancing effect. And so they've been leveraged to facilitate different sorts of applications. So much earlier work, really kind of pushed by Northwestern, was in facilitating different existing casting approaches. So this included slip-form paving, where conventional slip-form paving requires a very, very stiff mix, intense internal vibration, to achieve that shape stability after extrusion, but that led to durability issues because there were trails or voids that were left due to those internal vibrating fingers. And so work by Cohesion Wang developed semi-flowable SCC that can consolidate under its own weight, so eliminating at least the need for the external vibration or the internal vibration, but then still exhibit that structural buildup for shape stability after extrusion. Also, nanoclays have been found to significantly reduce SCC formwork pressure. So SCC is a highly flowable mix of very low yield stress material, so it can start to approach hydrostatic, so assuming complete vertical to lateral transfer. But SCC is also a material that can exhibit thixotropy, structural building, so that profile is less than hydrostatic, but if you enhance the thixotropy, you can reduce that even further. And work by Jae-Hyun Kim, Shaw, showed that with a small amount of nanoclay, 0.3%, you can substantially reduce that lateral pressure buildup. And this was measured through a lab-scale formwork pressure device. And so, you know, interest in nanoclays has really been increasing because of 3D printing. So these properties can be very beneficial for achieving shape stability immediately after extrusion in extrusion-based 3D printing. So, you know, in all of these applications, we're going to be systematically utilizing SEMs. And at the time of the study, I think we noticed that there really aren't very many studies that look at the effect of nanoclays and how they interact differently with OPC versus SCMs like fly ash and slag. And so that's what motivated this work. There was really no direct measures. So I did some literature review in preparation for this. So our study was back in 2018, and there's still very limited studies that, again, directly compare. So this is an example of a study that looked at the effect of different substitutions of SCMs and then the addition of different levels of nanoclay. And generally, I would say they saw similar effects on both the fresh and hardened properties. But then this is a study on geopolymers, which is a little different, but they looked at different proportions of slag and fly ash. On the left is 30% to 70% slag, fly ash, and then on the right is 50-50. And so if you look at the base mixes, so this is shear stress profile, so this is a rheological characterization. So some measure of viscosity. And so the base mixes are indicated by the red line, so very close. The axes are consistent. But then as you add nanoclay, you see that the effect is very, very different. So, there could be an effect of the binder system. And so we decided to look at this more carefully as well. And also you'll notice that CNTs are in the title as well. So nanoclays are primarily used as a Rheological modifier. But in mixed design development, you would expect that you're going to start to incorporate other materials, maybe CNTs, to enhance mechanical properties. So you would expect that these materials will be used in combination, and because they're both kind of like rod-like, we thought CNTs would be an interesting one to investigate. Okay, so getting into the study, so these were the binder components, so OPC, a blast furnace slag, and fly ash. I included the specific surface area and also the PSD on the slide. And a few things I'll point out is the slag is slightly finer than the OPC, and then the fly ash incorporates some coarser particles. And so to limit the number of mixes that we would be testing, because what we really want to do is compare OPC versus a blended system. So what we did was we tested the 28-day compressive strength of mixes that were composed of 50% OPC and then different proportions of fly ash and slag. So that's what's plotted there to your left. And so the horizontal line indicates the 100% OPC. So around 25% fly ash slag, we get comparable strength, and so that's what we went with. So we're going to be comparing 100% OPC and then 50% OPC, 25% fly ash and slag. So these are the nanomaterials, just some details. There were multi-walled carbon nanotubes, 90% carbon purity, those are the dimensions. And based on the work of Konsagudos, Metaxa, Shaw, we added 0.01% CNT by mass of cement, and then dispersed via ultrasonication and mixing water with the use of a surfactant, which was a PCE. With the nanoclay, polyborskite, attapulgite, we labeled it as Cal on the paper, so I stayed consistent in that way. So those are the dimensions, like I mentioned, and then we added at 0.3% by mass of cement and just dispersed them in water in a blender. And because they're highly hydrophilic, that's sufficient for lab scale study. And that's based on our own previous work. In terms of the mixes, so for shear rheological characterization and compressive strength, we tested mortars, and for tensile strength, we tested paste. The compressive and tensile strengths were based on standards, and the next slide I'll tell you a little bit about the shear rheological characterization. So the table, there isn't too much new information. Basically, OPC system, blended system with CNT addition, clay addition, or the combination. One thing I do want to point out is that for the CNT dispersion, we did incorporate a surfactant, and so we just added that to all our mixes for consistency. Okay, so a little bit about the shear rheological protocol. Everything was tested in a temperature-controlled stress-controlled rheometer in a parallel plate geometry with a 60mm diameter and a gap size of 4mm because we were testing mortars. And we did have sandpaper adhere to the surfaces to minimize slip. And so the protocol is shown to your left. So like a typical protocol, we added a pre-shear rest period, and then we introduced a linear ramp up and down to obtain a flow curve response. We just use the bigger models, the down curve, and so the intercept is the dynamic yield stress and the slope is the viscosity. So those were the key parameters. In addition to that, we also tested adhesive properties. So we performed the tack test immediately after that step, all on the rheometer. So we just moved the vertical plate up at a constant velocity at a very slow pace and obtained a measure of normal force evolution. And the peak force is taken to be a measure of static cohesion. So that could be related to yield stress. Okay, so these are the results. So first pointing out just the base mixes. So on top is plastic viscosity and the bottom is yield stress. And so for yield stress, there's really no measurable change between these blended systems. And with viscosity, there's a little bit of a change, but it's not substantial. And it's because there's a lot of factors at play. So some factors are increasing these parameters, some are decreasing. And so just kind of going through some of what's going on. Lower specific gravity of the SCMs results in a higher solid volume fraction, higher specific surface area, and then the angular geometry of the slag, enhancing friction, all would increase these parameters, while elution effects of the SCMs, the spherical shape of the fly ash having a ball bearing effect, and also the coarser nature of the fly ash all would drive these parameters down. Okay, so now getting into the nanomaterials. So the CNTs had opposing effects on viscosity and yield stress between the two systems. So if you look at yield stress on the bottom, it increased that parameter for the OPC, but then it led to really no measurable change in the blended. With plastic viscosity, it increased, and OPC decreased in the blended. So that's not really what we were expecting. I think what we were hoping for was no change, because this is a study by Patagoutos, Metoxen, and Shaw again, where they showed that with a highly dispersed system, your rheological properties shouldn't change. So this is a very sort of striking result, where the black curve indicates the mix without CNTs, and then the green is with incorporating CNTs without dispersion or sonication, so the viscosity profile bumps up, but then once you sonicate or disperse them, it goes back down to the base mix. And so taking those results, one thing that can be happening is that we're not sufficiently dispersing the CNTs. We followed, the recommended protocol, but there can still be dispersion issues. So that's one thing that we are attributing this to. But in any case, we're seeing different effects between OPC and blending, and that's something to take note of. Similar observation with the clays. So the clays did increase yield stress and decrease viscosity in both systems, as we would expect, because clays increase structural buildup and they exhibit shear thinning, but to different degrees between the systems. So again, we're seeing different behaviors in the blended systems. We're not really sure why we're seeing these behaviors, but in any case, it's something to take note of in mixed design. So perhaps in the blended systems, you would just need to incorporate a higher dosing. Combining these two, they just seem to have a superimposing effect. So if the additives increase the parameter, or they both increase the parameter, then it leads to an overall higher effect in the combination. If they had contrasting effects, then it netted out to a zero effect. So that indicated to us that there's minimal interaction between these additives. So we did measure static cohesion, so the raw results are on the top. And so what we found was they had the same trend as our yield stress measurements. And that's what we present in the bottom here, where through this equation you can relate yield stress to static cohesion. So that's what we did. And so we're presenting static cohesion that was directly measured via the tack test. So those are the darker bars, and then the lighter bars are calculated through our shear rheological measurements. And so you'll notice that the trends are similar, which is good, but the measurements through shear rheology are much lower, and that is likely because we know better now. We should have used static yield stress versus dynamic yield stress because that would be more closely tied to cohesion, and in that way that should bump up the values more. But in any case, the trends are similar. Okay, so now going into mechanical properties. So on top is OPC, and then the blended on the bottom. So we're reporting 7 and 28-day strength, but I'm only going to focus on 28-day. So just regarding the base mixes, lower compressive strength in the blended system, as we would expect due to dilution effects. And overall, CNTs, clay, and the combination did increase the 28-day strength in the cement mortars. So that was more of a measurable, substantial difference, I would say. But there was less of an effect in the blended. So regarding these two additives, the clays are primarily a rheological modifier, and with the CNTs, I think the effects are primarily on properties like stiffness, flexural strength, strain, energy capacity. So we weren't necessarily expecting an increase in compressive strength with the CNTs, but that seems to be measured in the previous talk as well. And there are mechanisms with which it could increase strength. So I know that, I think Professor Shaw showed it in part 1, where there's shifts in the phase distribution. So that refinement of the microstructure may be leading to that increase in compressive strength. Attapulgite clay, the same story. There is work that does measure an increase in compressive strength, and that can be tied to either improvement in suspension stability, or there are calorimetric results that support that there's influence on cement hydration as well. So we did see increases, and there are potential strengthening mechanisms, but these effects are not captured in the blended. So just again with the theme of different effects depending on your binder system. Finally, tensile strength. So these are just 28-day strength. And so looking at the base mixes, the same, where we see lower tensile strength of the blended system compared to OPC due to dilution. So looking at CNT, they did slightly increase 28-day strength in both systems, OPC and the blended. But I would say it's not on par with results of other groups, so we would expect maybe a higher increase. That was not captured, but again, we'll tie it to potential issues of dispersion. But again, seeing slightly different effects on the two binder systems. And this was kind of unexpected, and we won't really understand it, but the clays also led to a substantial increase in tensile strength in the OPC, not so much in the blended. Don't really understand that, but again, different effects. So that's kind of the main takeaway. So it kind of captures it pretty well here. So OPC versus the blended system, and then the effect of these additives on their own or in combination on each of the measured parameters, and they're very different. So again, that's pointing to, depending on your additive and depending on your binder system, you're going to have to think about what the effects are going to be. And what we found is that we would expect different degrees, but in some cases we saw completely different effects, so increase versus the decrease. So something to consider for future work, I think. Okay, so OPC and blended systems exhibited similar rheological properties, but each of the additives led to differing effects. So clays led to an overall increase in yield stress, decrease in viscosity in both systems, but to different degrees, while the CNTs had opposing effects depending on the binder system. And combining these two rheologically led to a superimposed effect. And focusing on mechanical properties, the attapulgite clay, although a rheological modifier, did enhance the mechanical properties, likely due to improvement in suspension stability. And the CNT effect, particularly on tensile strength, was not as significant as expected, but we're tying that to issues of dispersion. And that's it. So just some acknowledgements. That's the relevant publication and the real person that did all the work, Dr. Sue Ma. Thank you, and I'll take any questions.